Hello, everybody. So today our um, video will deal on the solution for example 4. But before that, let me just briefly go back to what we have discussed so far. Last video, we introduced fugacity, and we said that it's important because we can use it for accounting for non-ideal behavior, and also we use it for equilibrium calculations, and also for um, phase equilibrium, and it's also related to chemical potential, which is an important property in thermodynamics that would determine the spontaneity and direction of chemical reactions and phase transitions. So in terms of phase equilibria, fugacity is important because of uh, it's important in processes like distillation, extraction, and other chemical engineering um, processes. So today we will dedicate this video on the calculation of fugacity and fugacity coefficient. Um, Particularly, we'll be using the steam table. So our component is it is not a mixture, but our substance is water. Okay, so water, and also um, we would use the equations for the gas and also the subcooled equation that for fugacity that we derived last meeting. Okay, so we'll also use the uh the one that we derived for here, that for fugacity of an ideal gas, and also for the subcooled liquid. Okay, so let's begin. I will be transferring the screen to the whiteboard. Okay. All right, so this is the problem. For H2O at a temperature of 300 degrees Celsius and for pressures up to 10,000 kilopascals, calculate the values of the fugacity and fugacity coefficient from the data in the steam tables and plot them versus pressure. So there's plotting involved. We need to graph. Um we can use Excel for the plotting. All right. Let's begin by writing the given in the problem, although it's very short. Okay. Given in the problem is the temperature at 300 degrees Celsius, or this is converting to Kelvin, 573 0.15 Kelvin, and also pressures up to 10,000 kilopascals. And then we're being asked for uh, values of to calculate Fi and Phi, okay, for pressures up to 10,000 kilopascals. So they did not specify, problem did not specify at which pressures, as long as we calculate it up to 10,000 kilopascals. And then plot Fi and Phi versus pressure. Okay, for the solution, um, we need to use the equations that we have established for fugacity, but it will be different for the gaseous part. Okay, for the gaseous part and the subcooled or liquid part. Okay, so if we have, say this is our, uh, let me draw a straight line. So this is the given pressure up to 10,000 kilopascal. So we need to make a a plot of, or we need to calculate values for fugacity and phi at different pressures up to 10,000. So we need to set a reference pressure, okay? And then we need to know the P saturation, right? The pressure at saturation point, right? So why? Um, so remember that below the saturation point at 300, a temperature equal to 300 degrees Celsius, below the P saturation, our water behaves as a gas, right? Is in the gaseous phase. However, above the P saturation, okay, um, it will behave as a liquid. Okay, so as we increase the pressure, at some point sub it will liquefy. Okay, so we need to know the P saturation, and for this part right here, okay, um, we use the equation for the gas, but for this part, we use the equation for the liquid. So the key thing is to first check, right? To first check what is the P saturation. And we can use the steam table. So let me open the steam table. All right. Hold on for a bit. Okay, this is the steam table. And look for the P saturation at 300 degrees Celsius. So this is the uh, temperature 300 degrees Celsius using the saturated property table, and getting the pressure. Okay, the saturation pressure is 8,592.7. So let's write that onto our, so this is um P equal to 8,000. Okay, hold on. 8,592.7 kilopascals. So this kilopascals. So we are more or less we are sure that okay, we're dealing with two phases. So we need to use different equations for each stage, right, for each part. Um, so beyond the saturation pressure, we need the to use the subcode equation. So for the gaseous phase, what equation can we use? So let's go back to the lecture slides. Okay. I'm showing now the lecture slides. Let's go back to the part where we um, derive the equation for fugacity. So first, we begin with the fundamental property relation, if you will remember this one. And then if we assume constant temperature, it will simplify to this one. And then for an ideal gas, the equation is simply RT over P dP. And then integrating, we get this equation. Okay, so I hope that you remember that. And we introduce fugacity. We said that for a real gas, we can represent the pressure, okay, as the fugacity, Fi. Um, so we use that equation. Let me move back to the whiteboard now. Okay. Oops. We would need now a reference pressure. Okay. Um, let's call that P star. Let's call the reference pressure P star. That's why it's already written there. So, writing two equations using that particular Gibbs free energy equation. One is at the given pressure, at the given pressure, our equation is G sub I is the integration constant as a function of t plus RT ln f sub I. And then our reference at the reference pressure G sub I is G sub I star is our integration constant plus RT ln f sub I star. Okay? We to read of the integration constant, we subtract. Okay, we subtract the two equations from one another. So that's G sub I minus G sub I star equal to, so this cancels out the integration constant, and we're left with the RT times the ratio, natural log ratio of Fi over Fi sub star. Okay, we isolate we isolate the natural log on one side, so that would give us 1 over RT times GI over GI star. Okay. But by definition, G is equal to H minus TS by definition. And we replace the G right here with this expression, H minus T times S. So our equation becomes ln Fi over Fi star equal to H sub I minus Hi star over RT minus Si minus Si star over R. Okay? And now this equation is useful to us. Why? In the steam table, we have values for enthalpy and entropy. So if we just need a reference to get the reference enthalpy and entropy at the reference pressure, and then for the given pressures, we can also read that from the steam table. Okay, and now we can calculate the uh, fugacity at the given pressure. Okay, so um, an important thing is to set the reference pressure. Okay, so if we want to set a reference pressure, it should be at the point where the reference pressure, because at this point we don't know the fugacity of the reference at the reference pressure. Okay, we don't know this value. Okay, um, but if we set the reference pressure where the gas would behave ideally, then we can assume that the fugacity at the reference pressure is just equal to the reference pressure. So remember, this is true for an ideal gas, right? This is true for any gas. So what is a good reference pressure, therefore? Um, w- at what pressure would a gas behave ideally? Okay. So remember, the gas would behave ideally as it approaches zero pressure. Okay. So we need to select a very low pressure in order to assume, to make this assumption. Okay. So that this would be true. But we also have um to take note that the temperature is 300. Okay, so at the at constant temperature, what is the lowest? Okay, what is the lowest pressure possible? Okay, for this gas? So how can we do that? We just simply need to look at the steam table again. So let's go back to the steam table. Okay, so our goal is to find the lowest pressure possible for this gas. Okay. So this is the steam table, and let's go to the superheated section, okay, where the gas would where water would behave as gas. And then look at the temperature 300. Okay. As you can see right here, based on the steam table, the lowest pressure is 1 kilopascal. So the lowest pressure available for the temperature 300 using the superheated table is 1 kilopascal. So this is what we will assume because um, it's a good assumption because it's the lowest pressure and we have values for the this one for the uh, enthalpy. So take note that we're not going to look at the saturated because we're dealing with the gaseous phase. So get the enthalpy here, which is 3000 plus, and the entropy. So take note of that. All right. So I hope that is clear. Let's go back to our board and write from the steam table. So the selected pressure is 1 kilopascal at 300 degrees Celsius. This is from the steam table, right? So um we write the enthalpy and entropy at 1 kilopascal and 300 degrees Celsius, and that is 3076.8 kilojoules per kilogram. However, for our purposes, it be worthwhile to write it as joule per gram. Just the same, we converted the units. So for entropy, it is 10.3450 joules per gram. Okay, so just convert the unit. Okay, so now we have the reference. Okay, going back to our equation, we have this value for the reference enthalpy and entropy. Our reference fugacity is equal to 1 because we assume that it behaves as an ideal gas at this pressure, 1 kilopascal. So this Fi star is 1 kilopascal. Okay. So now we iterate using different pressures. For different pressures, we would read the enthalpy and entropy. Okay. So let's do that. I will um, make using Excel, I will make a worksheet wherein I just copy paste that so no need to type again. I would make columns on the temperature, pressure, enthalpy, entropy. And for the uh, fugacity and phi, okay, these are the columns that we need to solve. The temperature is just the same right throughout. For the pressure, let's begin at 1, okay, because that's our reference pressure. And then our last pressure is 10,000. So because the problem asks that we calculate up to 10,000. We also need, it will be worthwhile if we include the saturation pressure, which is 8,592.7. Right. And then below that, let's just arbitrarily select some pressures. So it's up to you. If you want more pressure, you can insert lines between this pressure. Like if you want to calculate for every 1,000, that's okay. That depends on you. But for this problem, let's stick with this 5 points, 6 points. So that again, this is our reference Pref. This is our PSAT. Okay. So we write the pressures that we obtained. Remember, this is our reference, and we already obtained this via the steam table. So just typing it here. And then for the rest of the values, okay, let's skip let's skip first to the P saturation. Is this something that we can read from the steam table? Yes, we can do that by reading, okay, the saturated properties. Okay, saturated properties at 300 Kelvin. Okay. So this is the line right here. This is the saturated table. And we have to use the vapor. Okay, we have to use the vapor because we're still at this stage dealing with the vapor. So we write the enthalpy and entropy as a vapor. So that's this last two column. Last column. So that's 2751. So we write that 2751. Let me double check if okay. All right. So 2751, and then for the entropy, it's 5.701. So this is the saturated vapor properties. Okay. And then for the rest, just read them from the superheated tables. I would leave that to you to make those enthalpy and entropy readings for the rest of the pressure. Um, but for now, for the interest of time, I will just copy paste what I have read earlier. All right, so this is um, the values. Okay, so now let's just focus on the vapor phase first. Okay, let's focus. For the subcooled, we don't have a table for that, and anyway, we don't need it. The enthalpy and entropy for the subcooled. So again, beyond the saturation pressure at 10,000 kilopascals, our water would behave already as a subcooled liquid. Um, so let's keep it blank. We don't need it anyway. We'll use a different equation for this one. Now let's calculate for the fugacity using a sample given pressure. Okay, let's say we want to calculate the fugacity for or at the pressure 4,000. Okay, let's do that. Using the equation, okay, using this equation, let's substitute the values. Okay, ln fi, ln fi over fi star is equal to substituting the values. Um, 2962 minus 376.8. This is joule per gram, and this is 8 over R 8.314 joule per mole Kelvin times 573.15 Kelvin, and this is S minus S star, which is 6.3642 minus 10.3453. So this is for the enthalpy, and this is for the entropy. And then uh divided by 8 joule per mole Kelvin. Okay. So far, let's check the units. What will cancel out? The joule will cancel out. The Kelvin This is joule per mole Kelvin, so this would cancel out. Uh, Kelvin would also, oops, this is joule per gram. Okay, joule per gram Kelvin. So joule will cancel, Kelvin will also cancel. So we're left with gram, mole per gram. So to remove that, because we want this to be a dimensionless quantity, we need to, as because we will going to exponentiate, okay, this quantity. So we multiply with the molar mass of water, which is 18.015 joules. My 5 looks like a J. So joules per, ups, not joules, grams per mole. Now we can cancel all the units. Okay, mole will cancel. Okay, and then the grams would also cancel. Okay, so this is now a dimensionless unit, and that value is actually 8.9. Let me just check it for a while. Okay, let me 8.1917. Okay. This is dimensionless. So if we take the exponential of that value, e to the e to 8 e to the 8.197, then uh, we get 3611, and then multiplying with our fi star, okay, which is 3611 dimensionless times 1 kilopascal, which is our fi star. We will get a pressure, a fugacity at 4,000 kilopascal, equal to 3,611. Okay. So, and this is at pressure. Oh, I didn't write it. Let me write it here at P. Okay, at P equal to 4,000. This is our sample. So 4,000 compared to the fugacity 3,611. So for an ideal gas at pressure 4,000, um, okay, it will have the same G, okay? But for a real gas, okay, the pressure is to have the same Gibbs free energy, the pressure is not 4,000 but 3,611, because the fugacity, okay, this is important, is equal to the pressure of an ideal gas which has the same temperature and molar Gibbs free energy as the real gas. Okay, so I hope that's clear. Again, so at the um, temperature, at the same temperature, and molar gives energy. Okay, at the fugacity is equal to the pressure of an ideal gas with which has the same temperature and molar gives free energy as the real gas. So that's why fugacity is like our representative pressure. Okay, so that's one way to interpret that. This is the pressure of an ideal gas with the equivalent molar Gibbs free energy and temperature as a real gas. Okay, so let's move on. Um, by first writing those values to our Excel sheet. So now I will write the calculate. We did not calculate for fee, so let's first calculate for fee. Fee is equal to mm, F I over P I. Okay. And that is 3,000 over 4,000. And that is equal to 0.9028. And now we write it to our, or type it. At 4,000, Fugacity is 3611 and fee is 0.9028. Okay, so, alright. So, as a shortcut, for the rest of the pressure, or even this pressure 4,000, you can just input a formula in Excel. Let me copy paste that. So this is just a formula in Excel that um, repeats the process for the other pressures. Okay. Uh, if you're not familiar with Excel, in order to set a cell or fix a cell so that it would not move, you simply need to put a dollar sign. Okay, so I will leave this up to you to exercise your Excel skills. Okay, so notice that at the reference pressure, since the values of um, the values of the difference in the enthalpy, this term is 0, and this one is also 0. If we, the exponential of 0, so e raised to 0 is 1. That's why this one is 1, and also phi will be 1. Okay, for phi, you can also set that. Okay, so in our calculation, it's 3,611 because we rounded off, but in Excel, when I inputted the formula, so it's just rounded off to 2 decimal places. So I just simply need to copy paste that um, to the other pressures. Okay, so copy paste that. Automatically, the formula will apply at the different, okay, at the different pressure. So please practice your Excel skills. Okay, so now that we are done with the gaseous phase, let me check first if we have the same answer. Okay, all right, so we do have the same answer as our handout. The next part is to deal with the liquid phase at pressure 10,000. Okay, so how can we calculate for the fugacity and phi at the liquid phase? Let me go back to our slide. Okay. So last lecture, we derived this equation, fugacity of a pure liquid. Okay, so this is our final equation, and we're going to use it at the pressure 10,000 kilopascal. Okay, let us rewrite that on our whiteboard. So at P greater than P sat, okay, use the equation for subcooled. Use fugacity equation for subcooled liquid. Okay? And that equation is Fi equal to Phi saturated times Pi saturated exponent or e raised to the value of V sub IL times P minus Pi saturated, okay, divided by RT. So this is our equation. Do we have everything that we need to calculate for the fugacity? Okay. For Phi saturated, what is this value? Okay, what is this value? We simply need to look out at our table, okay, here, okay, at the saturation pressure. This is Phi saturated. So copy that, 0.7846, 843. So this is 0.7843. How about our Pi saturated? It's simply 8592.7 kilopascal. So this is our saturation pressure. So this is already known. We know that this is the given pressure, which is 10,000. We will, or any, if you still want to calculate between 8,592 to 10,000, for example, you want to calculate at 9,000, then please do so. But for this example, let's just use 10,000. And then we also have R and T, but we do not have V I sub L, which we can easily obtain from the steam table. From the steam table at 300 degrees Celsius. Okay, read it. I won't uh, detail that. So you just please read it. And this value is 1.404 cm cube per gram. We need to transform it to joules to make our life easier. So just multiply it with 18.015 joules, grams per grams per mole. I'm always confused with the molar mass, so that would cancel out, and we will get 25.28 cm cube per mole. Okay? Alright, now we substitute everything into our equation. Here, we substitute it. So Fi, so Phi is 0.7843. Oops, oops. Okay, let me. And then times 8592.7 kilopascals times the exponent of um 25.28 cm cube per mole times 10,000, our given pressure, minus 8592.7. Alright, so at this point, we need to transform kilojoules to kilonewton per meter squared. So this kilojoule per, this is kilopascal, sorry. We need to transform kilopascal into its basic unit, which is, this is kilopascal, so that's kilonewton force over area. So kilonewton per meter squared, right? And then, uh, so hold on. Let's first settle everything. Why can't I make a straight line? Okay, so at the bottom, we write 314 joules per mole Kelvin times 573.15 Kelvin. All right. Our goal is to make this quantity dimensionless. How can we do that? Um, let's get rid of the joules by by making it kilojoules. Okay. Kilojoule, 1 kilojoules is 1000 joules. Okay. And then convert the kilojoules into its kilo basic form. So that's 1 kilonewton meter is 1 kilojoules. Okay. Convert the cm cube to its uh 2 meter. So 1 meter, 100 cm, and then you have to cube that. All right. Now we cancel. Cancel. Mole will cancel. Kelvin would cancel. Kilojoules would cancel. Cm cube would cancel. Kilonewton would cancel. Okay. All right. So meter cube would also cancel. Meter squared here, meter here. So this is meter cube, canceling the. So we now have a dimensionless value, I mean quantity, and Fi is equal to 6, oops, 6789.75 kilopascals. Okay, and phi is 6789 over 10,000 is equal to 0.679 T. So we write that back into our Excel table, 679T, 6 and 0.679T. Let's check here if it's correct. P is 6789.67. Yeah, it's correct. And this one is liquid. Okay. Uh-huh. So what's the next step? We need to graph to make a plot. Something that would look like this one. Okay, this is our goal right here. To plot the fugacity against the and phi against the pressure. And as you will notice, okay, we have two axes. The left one is for the fugacity which has a unit of pressure, and the right side is for phi, which is dimensionless. All right, I hope you have very good Excel skills, but I will also demonstrate to you how to plot this. Uh, we insert a scatter plot. Scatter, is this the scatter plot? Should be a scatter plot. Oops, wrong. Insert a scatter plot. Let me zoom out for a while. Okay, so this is our scatter plot. And then right click, select data. Then click add. I add. The series name is kilopascal. Sorry. The series name is, click the cell of fugacity. And then for the x values, select the pressures. And then for the y value, select the fugacity. Okay? And then add another series, this time for phi. X values is the pressure and the y values are for phi. Okay? So right now, it doesn't look good because we're just using one axis. We need to transfer phi to the a secondary axis on the right, and we can do that by opening the, okay, I can see it because of the zoom, the chart design. Because of the zoom, it's, hold on, I will just, okay, hold on, please. Zoom is covering the buttons. Chart design. Okay, this is the chart design, and then under chart design, select change chart type, and then select combo, and click P a secondary axis. Okay, and then for the chart type, you have to convert them to scatter. This one, scatter with straight lines, the both of them. Scatter with straight lines. Take note, it should not be line. That's a different graph. It should be scatter with straight line. Okay. All right. So more or less, it's starting to look similar with our plot right here, right? Starting to look similar. Okay. So we need to fix the graph for aesthetic purposes. But this already is your answer. So we want to remove the space here. So let us format the axis and make it up to 10,000. The pressure up to 10,000. And then we want to make, similar with the graph, we want to make the vertical axis by up to 7,000 and this one up to 1. So more or less, it's beginning to look like our graph. And then you can also make a plot. So let me show that to you. For the, right now what we have is the solid black lines. And that's already the answer. But you can make a plot of the Fi saturation, which is, the value for that is this one. At saturation pressure, this is the Fi saturation, 6.738. So you can make a plot of that, Fi sat. Just copy that because it's a straight line. Copy all the values as Fi sat. And then there's also another plot here by the, where the fugacity is equal to the pressure, the given pressure. Okay. We can also make a plot for that. Okay. So I'll just show you the final product. So please, you can figure it out on your own. This is the attempt. Okay. However, so this is the FI sat. It does look like the one from the solution. Let me screenshot that. Okay, so hold on please. Let me go back to the Excel and then right there. All right, so it does look like the solution. The only problem is that I don't have a point at this section. So this line should actually go straight and then sit diagonally and then to the right. So if we have a point here, which is 6738.92, but that means we need to interpolate the enthalpy and entropy, which I do not want to do anymore. Just do it yourself. Insert a pressure here after 6,000. The pressure is Fi sat, which is 6738.92. You need to interpolate for the H and S, and then calculate for the S, for the Fi, and for the fugacity and phi. You'll see that it will look like something similar to this graph right here, the dashed line. Okay? So I hope that the solution is clear. So by the way, for the solution, they express the pressure um, in terms of 10 to the minus 3 kilopascal. So that's okay as well. All right. This ends the solution for example 4. I hope it's clear. For the next lecture, we will do some discussion and also a an example problem.